Alright, in this second video on pH titrations, we're going to look at a titration between a strong base, in this case sodium hydroxide, 0.200 molarity, with a weak acid. And the weak acid we're using is formic acid, 0.1 molar, 25 milliliters, sitting in a beaker. The formic acid is a weak acid with a Ka value of 1.8 times 10 to the minus 4. We're going to calculate the pH during the titration at various points, from 0 milliliters all the way up to 15 milliliters. If you think you know what you're doing, you can pause the video and try this yourself and then just check your answers as we go. So, a strong base with a weak acid. The first part of the titration is when we've added 0.00 milliliters of strong base added. So here we're really not yet starting the titration. Here all we have is 25 milliliters of 0.1 molar formic acid sitting in our beaker, and we want to know what's the pH value. So this is really just a weak acid pH question. So jump in and set it up and solve it. So the weak acid, formic acid, will react with water. It's dissolved in water, and Bronsted-Lowry definition, the acid will donate hydrogen ions to form hydronium, and then you'll be left with the conjugate base, formate, HCOOH-. We have 0.1 molar formic acid. Water we can ignore because it's a liquid. There is hydronium initially present in pure water. It's 10 to the minus 7 molarity, but that's so small we just almost always ignore it. There is no formate ion initially in the solution. And now we know this is a weak acid, so it's going to ionize only partly. So we'll say loses X. In a 1-to-1 ratio, these will gain the same amounts, X. And so in the solution, you've got 0.1 minus X, the concentration of formic acid. You have X, the concentration of hydronium, and you have X, the concentration of formate, the conjugate base. The Ka value is 1.8 times 10 to the minus 4. That's equal to the concentration of your hydronium times the concentration of your formate ion. This is just the equilibrium expression for the reaction over HCOOH concentration. So 1.8 times 10 to the minus 4 is equal to X times X, or X squared, over 0.1 minus X. And now you can solve that either using the approximations method. We could say that since the Ka value is so small, we could assume that X is much less than 0.1 and then solve for this X in the numerator. Or we could use the solver on the graphing calculator, and that's what I'll do real quick here. So I'll press the math button, I'll go down to the solver, I'll press the up arrow and clear the equation that was there. So equation solver 0 equals. When using the solver, you have to enter your equation in the form 0 equals, not Ka equals. So we'll just take the Ka value and move it to the other side of the equation. We'll subtract it from both sides. So we'll have X squared divided by bracket 0.1 minus X, close the bracket, and then minus 1.8 times 10 to the minus 4 equals, and then we give the calculator a guess. We almost always just say X is close to 0 as a guess, and then alpha solve. So 0.0042 is the value for X. So from the solver, X equals 0.0042 molarity, which is the hydronium concentration. Therefore, your pH is negative log of the hydronium concentration, negative log 0.0042, and our pH is going to start off small because there's an acid present. So negative log 0.0042, 2.38 is the value of the initial pH in the beaker. So when no base has yet been added, the pH is just a weak acid pH, 2.38. So now let's begin the titration by adding 5 mils of the sodium hydroxide. Alright, so part B, after 5.00 milliliters of 0.200 molar sodium hydroxide has been added. What's the pH now? Well, adding the strong base to the weak acid is going to result in a neutralization reaction. So let's write out the equation for the neutralization reaction. The weak acid is HCOOH. Some people would just say HA. They would represent it as a generic formula, HA. And it reacts with the strong base. Now you could write sodium hydroxide, but a smarter thing to do would be to recognize that this is a strong base and therefore is completely ionized, and then rather than write a molecular equation, just write the net ionic equation. Leave out the spectator ion, so leave out the sodium ion. So it's really reacting with hydroxide ions from the strong base. Producing the H from the acid goes with the hydroxide to give me water, and that'll leave me with formate, the conjugate base. So now we're going to use millimoles in this ice table. The reason we're not using molarities is simply because we're adding a volume to a volume. We had 25 mils of the formic acid initially, and we're adding 5 mils of the base, so there's going to be a dilution happening, and I don't want to have to deal with the dilution. So instead I'm going to use moles, or in this case millimoles, in my ice table. So if we had 25 milliliters, I'm using N equals C times V as my little formula. The concentration of the acid was 0.1 molarity, and we had 25 milliliters, the volume. So if we leave the volume in milliliters, 25 times 0.1, we get 2.50 millimoles of the acid. This base has only one hydroxide in its formula, so in a 0.2 molar sodium hydroxide solution, there would be 0.2 molar hydroxide, and we've added 5 milliliters. So 5 times 0.2, C times V, we get 1 millimole of hydroxide. The water will ignore. We'll assume there was no formate initially present, so we're ignoring the little tiny bit that has ionized originally. And now this is a neutralization reaction. We're not going to prove it here, but the Kc value is equal to the Ka value of the weak acid divided by Kw. That can be shown, which is a very large value. Neutralization reactions always have large Kc values. That means one of these two things will be used up completely. So -1, -1, the smaller number in a 1-to-1 ratio is the limiting reagent, and +1. So we have 1.50 millimoles of formic acid left. The hydroxide was completely used up, and now we have 1 millimole of formate. So now we notice that in our beaker we have a mixture of formic acid, weak acid, with formate, the conjugate base. And that is the definition of a buffer. When you have a mixture of weak acid with its conjugate base, you have a buffer. We derived in class the Henderson-Hasselbalch equation, HH equation, which said the pH in a buffer is equal to pKa value of the weak acid plus the logarithm of the concentration of the conjugate base, in this case formate, over the concentration of the weak acid. That was the Henderson-Hasselbalch equation for buffers. And so formic acid had a Ka value of 1.8 times 10 to the minus 4. If we take the negative log of that, negative log of 1.8 times 10 to the minus 4, we get 3.74. That's the pKa value. So 3.74 plus the logarithm. Now, although the Henderson-Hasselbalch equation specifies concentrations in this ratio, because these two substances are dissolved in the same solution, their volumes are equal. So if we could take the total volume right now, which is 5 mils plus the original 25, the total volume is right now 30 milliliters. We could divide each of those by 30 to get their concentrations. But because the volumes are the same, we can actually omit that step. The ratio of millimoles will be the same as the ratio of concentrations if the volumes are the same. Okay? Prove that to yourself mathematically if you have to. So I can just take 1 millimole and put in 1.5 millimoles here. So 1 millimole of the base, 1.5 millimoles of the acid. So now grabbing a calculator, 3.74 plus the logarithm of 1 divided by 1.5. Notice that you had more acid than base, so the pH is going to be lower than the pKa value, 3.56. So, pardon me. So our pH after the start of the titration is 3.56, and we had a buffer in the beaker at that point. Okay. Now let's keep titrating. Where 6.25 milliliters of base have been added. So after 6.25 mils of NaOH. Now that's not a randomly selected number, as you'll see in a minute. That number is carefully chosen here. The reaction again, the neutralization reaction, the weak acid reacts with the strong base, hydroxide, to produce water and conjugate base, HCOOH-. We had 2.50 millimoles of the acid, 25 mils of 0.1 molar, and now 6.25 milliliters times make sure I get this right, times 0.2 is going to be 1.25 millimoles of hydroxide. The concentration of the base was 0.2 molarity. And then we can ignore water and 0. Now notice what I said about this was carefully selected. This is not just before the equivalence point still. We can tell it's before the equivalence point because we've still not added enough hydroxide to neutralize all the acid. But this is actually exactly halfway to the equivalence point. With 2.5 millimoles of acid, we've added half of that of the base. So this is a very important point in the titration of a weak acid with strong base, the halfway point to the equivalence point. You'll see why that's important mathematically in just a moment. So we lose 1.25, we lose 1.25, we gain 1.25. So we have now equal amounts, 1.25 millimoles of the weak acid and its conjugate base. Now why is that so important? Well, we still have a buffer, and so we'll use the Henderson-Hasselbalch equation again. So the pH will equal the pKa value, 3.74, plus the logarithm of 1.25 over 1.25. Now notice, because these are equal, this ratio now becomes 1, and the logarithm of 1 is 0. So when you are halfway to the equivalence point in a weak acid strong base titration, your pH will equal your pKa value, 3.74. That's very important to note. So because we're halfway to the equivalence point, pH is equal to pKa, 3.74. That's true in weak acid, strong base titrations. It's also true in weak base, strong acid titrations. So this is buffer halfway to equivalence point. Ten mils of base. If you think you know what you're doing, go ahead and set it up. So the acid reacts with the strong base, water, and conjugate base. We had 2.50 millimoles, and now C times V, we have 0.2 times 10, we've added 2 millimoles. So we're still before the equivalence point, but we're getting close now. Minus 2, minus 2, plus 2, 0, 0.5. We're almost out of acid right now, but we still have some, and we've got lots of conjugate base. So we still have a buffer, weak acid mixed with its conjugate base, so we can use our Henderson-Hasselbalch equation. pH will equal the pKa value, which was 3.74, plus the logarithm of the base concentration, or in this case base millimoles, over the acid millimoles. But notice, because we have more base than acid, the pH now is going to be above the pKa value. So 3.74 plus the logarithm of 2 divided by 0.5, we get now a pH of 4.34. So we've just gone past the pKa value. Now 12.5 milliliters, if you're following mathematically, you can see why that's an important number. So 12.5 milliliters of 0.2 molar sodium hydroxide. Set up your ice table. The formic acid reacts with the strong base to produce water and formate ion. We have 2.50 millimoles originally of the acid, and now 12.5 times 0.2, we've got 2.5 millimoles of base. So we've reached the equivalence point. This is important. So the reason it's important is because, as you can see right now, we have destroyed our buffer. Okay, we've overcome the capacity of our buffer. We have only weak base left in the solution. There's no more weak acid. So all we have is weak base. Okay, so this is at the equivalence point. We have just the weak base. This weak base is not from a strong acid. If it were from a strong acid, it would not affect the pH, and we would simply say the pH is neutral now. But this weak base will affect pH. It's going to have a pH above 7. So we have to do a weak base pH problem. So we'll take the weak base, the formate ion, let it react with water in a weak base pH problem. It accepts hydrogen, forming formic acid again, and hydroxide ions. We're going to need two things. We need to know what the concentration of the weak base is, so we can put that in the table here, and we need to know the Kb value for the weak base. Its concentration is moles divided by volume, or millimoles divided by milliliters. So 2.50 millimoles divided by 12.5 plus 25, we have 37.5 milliliters. The 25 milliliters of acid that was there originally, plus the 12.5 mils of base that we just added. So 2.5 divided by 37.5, 0.0667 molarity. So there's our concentration of the base. The water we can ignore. We'll ignore the little bit of hydroxide that's in pure water. We know it's a weak base, so minus x plus x plus x, 0.0667 minus x, x, and x. So now we need to know the Kb value for this base. We can get the Kb value by taking Kw divided by the Ka of its conjugate acid. So that would be 1 times 10 to the minus 14 divided by the Ka was 1.8 times 10 to the minus 4. So the Kb value for this base is 5.6 times 10 to the minus 11. So taking our Kb expression, the Kb will equal the concentration of the formic acid times the hydroxide concentration over the formate concentration. 5.6 times 10 to the minus 11 will equal x squared over 0.0667 minus x. I'll use my solver on my calculator. So math solver, go up and clear the old equation. So we want to type in x squared divided by 0.0667 minus x, and then subtract the Kb value. I'll use 0 as my guess. Alpha solve 1.9 times 10 to the minus 6. And that's my hydroxide concentration. So now we can say the POH, negative log of the hydroxide concentration, negative log of 1.9 times 10 to the minus 6, 5.72. And so the pH will be 14 minus the POH, 8.28. And notice that the pH is basic because of the salt that's in there, 8.28. So this was a buffer. This was at the equivalence point where we have a basic salt. The salt was sodium formate, and although sodium doesn't affect pH, formate makes the pH basic. So now let's go past the equivalence point and add 13 mils of base. So this is part F. After 13 mils of sodium hydroxide. So we have the formic acid reacts with our strong base to make water and formate. We had 2.50 millimoles of the acid, and now we've got 2.6 millimoles of hydroxide, 13 times 0.2. So now we can say minus 2.5, the smaller number, minus 2.5 plus 2.5, and look at what's now left in the flask, or in the beaker. We have leftover 0.10 millimoles strong base, and we have 2.5 millimoles of weak base. So we have right now a mixture of strong base and weak base. Now you have two choices here you can use to go forward. There's a fast way and there's a long way to solve this. The longer way to solve this would be set up your Kb reaction again, like we have down here. You'd find out the concentration of that base by dividing by the total volume, and you'd put that here. You'd find out the concentration of the excess hydroxide by dividing again by the volume and putting it here. And then you'd do a weak base pH problem, but you'd have some initial hydroxide present. It would not be zero. You'd solve it the same way that we did above. If you did that, what you would find is that the amount of extra hydroxide from the weak base is so small that essentially it doesn't affect the pH. So basically we can ignore the weak base when it's mixed with strong base. The weak base will not significantly change the hydroxide concentration in the solution. So all we're going to do now is take the excess strong base and say the concentration of hydroxide is moles over liters, so 0.1 millimoles over 25 plus 13 is 38 milliliters at this point. And so 0.1 divided by 38, 0.0026 molarity. That's our hydroxide concentration. I'm running out of room here, so I'm just going to say that POH is the negative log of this number, 2.59, and your pH will be 14 minus the POH, so 11.41. Okay, so when you are past the equivalence point and you have leftover strong base and leftover weak base, you just ignore the weak base, take the strong base, find its concentration, get your POH and your pH value, so 11.41. Alright, I'm going to actually stop there. So this is after the equivalence point. We had excess strong base. So you can see in this problem of a strong base with a weak acid, there's really four major points in the titration that have slightly different ways of finding pH. There's the original before the pH started, where we had just a weak acid present. There was at the equivalence point, where there was just a weak base present. There was before the equivalence point, where we had a buffer and we used Henderson-Hasselbalch equation. And then there's after the equivalence point, where there's excess hydroxide and we ignore the weak base of that situation. You might argue that the halfway to the equivalence point is also important, because there the pH equals the pKa value. If you were to graph our results, you'd see something like this. So volume of sodium hydroxide versus pH. The pH would start off low because there was acid in the flask. You'd see an initial little jump in pH and then a gentle rise like that. When you reach the equivalence point, there'd be a jump like this, not quite as steep and sharp as a strong base titration with a strong acid, and then a plateau again like that. pH at the equivalence point, in the midpoint of that jump, in a weak acid strong base titration is always going to be above 7. So 7 is neutral. In a weak acid with a strong base titration, you're always going to have the conjugate base of the weak acid present, and that weak base will make your pH at the equivalence point basic. So in our problem, it turned out to be 8.28. That's the way to tell, looking at a graph, that you're titrating strong base with weak acid. If the pH at the equivalence point is above 7, your acid was weak. If it's equal to 7, your acid was strong. So there's the distinction between a strong acid and a weak acid pH titration with strong base. So I hope that helps. Some problem solving for pH titrations. That's definitely going to be on your test and definitely on your final exam.